very few codes. Okay, the scheduler. I cannot show you the scheduler code, right? I will kill all people here when I show the scheduler code, except for the Init class. Okay, Init class will see the scheduler code. Regular class, I don't show it. I will give you high level idea. So this one point that this chapter get few programs. Second, I cannot show you the real stuff. Later on you will understand. Okay, so what exactly means the chapter on process organization and scheduler? Let's take a look at this diagram. I draw it beautifully, okay? You have many processes, as you can see here, seems to be unrelated, okay? But as a matter of fact, inside the kernel, so this is the blue zone here, the kernel look at it as a hierarchy. The hierarchy is a tree with only one root node. Only one root node. Later I will introduce the root guy to you. And this is the big tree here. This is I just draw it in a binary tree. It's not a binary tree actually. It's an n-way tree. Okay? And the tree has certain level, meaning that different level of parents-child relationship there. And this is the way kernel organizes a bunch of processes. But when it goes to the scheduler, what does scheduler means? Scheduler is actually a resource controller. He is a guy. Try to pull a process in this area into the CPU and let it to run for some microseconds and put it out again, put another guy in. Okay? So here, what is it? It's not a tree, right? I draw it as a tree. The tree itself is just a parent-child relationship. It's not about its priority. These are the priority levels. Okay? In a real scheduler, we have priority levels. Different priority levels may have a higher, maybe this guy has a higher weight to get into the CPU. This guy may be a smaller weight. Okay? If you're impatient, I want to play with a scheduler, go ahead with this call. What is it? Nice. Okay? Take a look. What is the description? Execute a utility with, utility means a process, with an auto scheduling priority. Wow, interesting, huh? But why this command called nice? It seems to be not very nice, right? You are changing this priority. Okay, so let me tell you why it's called nice. Its true meaning is be a nice guy. You can always decrease your priority using this call, unless you are the roots. Okay, you are the roots, then you are nice to yourself. Okay, if you are not the roots, you can only be nice to other people. Okay, you can try that. You can try that. How to measure the difference? You write infinite loop, not infinite loop is sucks. Okay, a loop for how many? Maybe 2 to the power 32 counts. Okay, from 0 to 2 to the power 32 minus 1. Okay, use unsigned long. Okay, then you can scan through. I hope that it will take you at least 10 seconds to finish it. Then you fire 5. You fire 5. Okay, in the background. Then you also fire one more with an alter priority. Then you will immediately see that that guy is very slow. I know you don't understand. Okay, I do it. Yeah. You know, I love this kind of crazy stuff. Okay? I'm not a nice guy. I will do this. You should know what it is, right? Okay, you don't like it? Okay. Boy, it's just the same. Okay? Don't care. Run. Good. Take a look at here. Sort by CPU. Find this. It's there. Okay? So how many battery I have? Oh, 89. Good. Okay. Send the background. So this symbol means send something to the background. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I find 10. Okay? Take a look here. Just wait. Approximately every guy take 30 something. Okay, so you imagine that when I have one more, then it will further decrease it into 20 something, right? Now I do this. Stop this guy first. Take a look at the main page of nice. Minus n means the increment, but actually it's not increment. I will try to set the test to be the lowest priority 20. And let's see what will happen. Nice, minus n, 20. Okay, fire. Oh, sorry, I skip a target. 40 something, not 20 something. Okay, and where is that test? I cannot even find it. Where can I find it? Let me. My computer gets stuck. Okay, I create too much. Yeah, maybe I make it into 3. Okay, and try again. I create too much. Okay, 3. 1, 2, 3. Okay, create too much. You wait for a moment. 1, only 2. What happened to my computer? Come on, I have 4 cores. Ah, yeah, good. You count. So I have 4 cores. So everyone get 90 something. Okay. Now I filed a 4th one. With a nice here. Wait for some time. What? Only 80. A little, just bit, but where are you? What happened today? Oh yeah, it is. Where are you? Why you? What happened? Lowest already. Positive. You can even found? No way. Okay, I surrender. I will do another way. What? Today is a bad day for me. I go to here. Yeah, this guy is most trustworthy. Mac is not very trustworthy in this case. I will bombard my own computer. Don't worry. This is my own computer. Make sure that it is a. What? So happen I have test stocks here. Okay. Wild one. Make test. Run. 1 guy, 2 guy, 3 guy. Take a look at the top. Okay, so I have 4 cores again in that computer. That is a Linux computer, not a Mac again. So 3 guys take up 100%. So if I launch a normal 4th guy, oh yeah, how can I open another terminal? Okay, I have to execute again. Top. So the normal 4th guy will take a 90 something, right? Let me fire one more. Now I input normal 5th. Then they cannot get 100, right? Because I only have 4 core. The 5th guy cannot take a core solely for it, so it's dropped for a bit. Now I change that 5th guy into a nice guy. All right. Yeah, that makes sense. Take a look here. 1%, 2%. Okay, so really a nice guy. Okay, don't ask me why Mac is not so nice. Mac is not nice, right? They are monopoly. All right, so this is nice, and this coincides what I said. Okay, about this priority. And priority scheduling is not easy to understand, okay? So we will try to use the last 30 minutes of this part in order to explain to you what exactly is a scheduler with priority. Okay? And now we will... Do you need a break? Need a break? All right, so break until 8 o'clock and it will be sold. I will usually do something bad to that Windows. Yeah, take a look. So I'm talking about the bootloader. Hey, what? Windows sucks. Okay. Yeah, it's not sucks. It's not power. No, not power. Okay. Yeah, it's booting up. So while it's booting up, we talk about something else. Okay. So master boot record. What is this about? Right. Come on. Okay. So it's about two things: the boot code, the partition table, and the boot code basically boot up something more. So just like a stage 1 booting and stage 2 booting. When stage 2 booting, basically you are trying to look for which kernel to boot. And what I'm going to show you in the Linux and the Windows is to tell you where is the kernel of Windows. Ah, interesting, huh? The kernel of Linux, usually you can find it here. Okay, so this is my Linux box. My Linux box here. I go to /boot. So this is Ubuntu. So these are the, we call it kernel image. Delete them and reboot your machine. You will never put it out. Yeah. Remember, it's reboot and reboot. Okay. Remove doesn't matter. Reboot, bye bye. Yeah. I will try it on a VM. Windows. All right. C drive and Windows. So I'm looking at a PowerPoint. I don't remember the path. So it is system32. The file name should be called KRN. Yeah, this guy. This guy. It's called a kernel. Okay, Windows kernel. Can you see this description? Let's do this. Double click. Hit double click. Yeah, it's crashed. No. What? Rename? Well, I cannot execute it. Why? Come on, baby. Execute. Yeah, it's got stuck. Yeah, I run as administrator. Yeah. Oh. Come on, give me something. Yeah, okay. Windows subs. I don't have permission. Okay, I'm not an admin. Okay.
How about rename?
Rename 應該 should be not okay. Yeah, I don't have permission. Disappointed. Right. I know. Try at your home. So this is a Windows kernel. Okay. If you go to Elite class, you already know what is Linux kernel. If you're not Elite class student, you want to try it out. The notes already on our course homepage. You can go home and try it by yourself. You can create your own kernel image and also delete it. Okay. There is nothing. Yeah, you have a VM, right? Now, this is the start of the system, right? You will boot the kernel, and the kernel will fix all the things. Boot up the driver connect to the hardware, initialize the hardware, initialize the memory. Then after all the initialization, we will create the first process. Yeah, the first process. Who is the first process? /bin/init. All right. I don't want to kill it. Okay. I remember some special signal will really kill it. Okay. Let me try. Kill PID1. Boom. Nothing happened. Okay. And no debug message come out. Okay. Kill it. Okay. Kill it. Nothing happened. Okay. So what is this guy? This guy is our invincible number one process, we call it init, okay? And with the PID equal to 1. And the kernel protects this guy with all kind of signals. You want to kill it, it won't get affected, okay? Because it's being protected, and it's here. Now this time it's not being protected. You can remove it. Go home and try it, okay? Yeah, rm/sbin/init, then say goodbye to your system, okay? And system will say that kernel panic, and then blah, 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 okay? Yeah, you can boot. Right, now what happened next? Next is, this is only for Linux. The next thing is, usually in a system, you will have a /etc directory, right? Usually. And usually, inside here, you will find the init.d directory. Okay, if your system don't have init.d, it is renamed into another thing. Okay. ls, there are a set of commands. The set of commands. This set of commands will be the first batch of things that the init process will try to start. So the init process, when it's being created, it will go one by one, or start this, okay, and start all the things here. Oh, the readme is not, okay, skeleton is not, but start all the things here, and it create the next wave of server processes. Service means not a server, but let's say that this guy is managing the power of your computer. What else? Some other guys like why there's a reboot, okay, very horrible. And this is a server, right? SSH server. So it will create all the processes so that it will enter the next phase, the login phase. Okay. After this, of course, delete them. Say goodbye. Okay. Don't always ask me what happened if it's deleted. Try it. Okay. No problem. Using a VM, right? Or do a snapshot of your computer and delete it. Okay. This is a way of learning. So all done by fork and execute. Okay. So this init will go to that directory. Look at it one by one. Oh, there's a SSH. Okay. So I fork and execute that SSH daemon. What daemon means server. Okay. And so on and so forth. Then your computer at last will show you the login screen. Okay. So this is kind of easy to understand. And their architecture or hierarchy, I should say, is something like this. For execute the SSH server, let's say you connect to the SSH server using the SSH terminal in your Windows, or just launch a terminal in Mac or Linux, try to SSH to another machine. The server receive it, will create a shell for you. If you are inside that shell called top, you will form this kind of a 4-layer of hierarchy. Now, how can you see the hierarchy? Very easy. There is a command to show. It's called PS3. Okay? So what is this? Let me pipe it. So just like a tree wheel, the first guy is the init. The init creates so many things. Remember this guy? I said it's about power, about computer power management. This guy is a web server. I start with web server. It's my computer. This get TTY is get. Shouldn't say get TTY, but TTY is a thing. Get is another thing. I don't know why the Linux guy love to combine this. I love to call it get TTY. Okay, it should be get TY. So this is the login screen. The login screen, 6 login screen there, and then a bunch of things get created. Where is my SSH? Can you find it? Can you find my SSH? Remember what I'm just executing. I'm executing PS3. Can you find my PS3 command inside that tree wheel? Here. Take a look. The SSH daemon, the server, I don't know why it's create some subprogram, create other layer of subprogram, create a shell, create the LAS as well as the PS3. Okay, so as to form a big tree here. And the big tree here is not funny. What is the meaning of not funny? You know, the big tree can get chopped off. What is the meaning of get chopped off? Like this. Let's say I'm running this guy, I have a shell execute the top. I don't know why, I detach this relationship. How? I put this guy in the background and type exit or log out. Okay? Log out, then I will kill the shell. Or maybe this is not a top is not funny, maybe while one loop. Okay? I will have while one loop here, and when I launch that while one loop, I kill the shell. Now this guy become an orphan. The orphan here, what will it do next? In Windows and in Linux, they do it in different way. In Linux, it will form a tree rather than a forest. Yeah, only one root. And in Windows love forest. Okay, and just I don't care. You become a new root. Thank you. That's all. Okay, this is the way that Windows handle it. Now in Linux, it will do one important job. We call it reparent. What is the meaning of reparent? You find this guy just got terminate this guy, and this guy become an orphan. Immediately, it will change the parent to the init. I can show you a proof. The proof is done by this program. Take a look at this program. Don't believe in my screen input. Okay, you know today I got some problem. Okay, so don't believe in this guy. Here, take a look at the code. Which part is a parent? Which part is a child? Who died first? I give it 1 minute. Or still remember the get PPID, the parent ID. All right. So how many bytes you will see? 2, right? One is from parent, one is from child. The byte here. Okay, so I guess you will understand that eventually both will gone. Who died first? Parent or child? Huh? Parent. Which part is the parent? This part? Yes? What? Yeah, if you say yes, yeah, go back and redo your assignment 1 page one. You must have some problem in your program. Okay. This is child, okay? The fault return 0 is a child. Huh? And the child keep on sleeping 5 times. Parent sleep for only 1 time. All right. So let's do it. R4, compile it. I only get 1 example in this computer now. Now run it. Don't ask about the order, but look at the ending phase. What this program reports about the PPID. Any idea? Can you get any idea about this? During this 1, 2, 3, 4, 5 longer outputs, okay? Don't ask why the prompt get up first, okay? It's very easy to understand because the parent died first, okay? If you don't get it, don't ask, okay? Later on, we can revisit the code. Now, this 5 long outputs, you find 2 of them here with what? With the parent ID equal to this guy, okay? Because this guy just died here, so when this guy tries to report its PPID, I mean, parent ID, is still the 30316. Okay? Although you look at the code, it's totally different, right? The code tells you that the parent only sleep for 1 time. How come the child report 2? Parent that is it should be gone, okay? It so happened that this guy dies a little bit later than the child tried to report the parent ID. Understand this point, okay? So that you will get 2. And after the parent died, you will become an orphan. Not you, sorry. It's that guy, okay? 317 become an orphan, and immediately you will find this change the parent to init. And the shell just pop up again because why? The parent here dies, and the shell only take a look at, oh, you have a parent process, and you have a process, and I don't know how big your family is. Whenever the process that I'm interested in die, I will give you back the prompt. So you will see the prompt show up again and continue to report PPID, but now switch to 1. What can you say about this? It's very interesting here. First of all, any question about this program that you don't understand, you want me to explain again? No? Alright. So what's the interesting point about this program? The interesting point of this program is if I have a process running on a shell and it's not foreground. When a foreground, Control C is die, right? It's in the background, okay? And then I terminate this parent. Will it die? No. I have a shell. I create a background process, okay? And its parent is the shell itself, right? I kill that shell. Will I also kill the child? No. This example tells you no. The parent dies, child is still there. Now, let's show it again with another example. Still remember this? While loop. Send it to the background. So this means send it to the background. Okay, so this is the test guy. Who is the parent of this test guy? We can use PS3 to take a look, but in Mac, it's kind of long here, right? So we have to look at it very slowly. Where are you, test guy? Wow. Okay, I forget about it. Test. You are here. Okay. So test is here. My parent of this test is the shell. Okay. Although I create this as a background process, its parent is still the shell. All right. Now you understand this fetch is still executing. Jobs tell me that it's still running. If you don't believe in it, take a look here. The activity monitor also it is still running. Now I type exit. Go. Gone. I kill the shell. Activity monitor. What does it say? Gone or here? Gone or stay? Stay. It stay. You kill the shell. Doesn't mean you kill the background. Okay? Now, what does that mean? That means that, hey, I have some process, okay, which I expect it will take 2 days to finish. Okay? Do you really, it took 2 days, okay, I open up my MacBook, okay, put it in a desk, and tell my mom that don't close it, okay? Don't remove the plug, okay, it will die. No, you don't need to do it, okay? You can close all the application, but before you close all the application, of course don't reboot it, okay? Close all the application, but before I send it to the background, okay? And you play your games, okay? It's still running in the background. It won't get killed, all right? And there is one special thing about Mac. Mac sucks this time, okay? This time is Mac sucks. I do it again. Let me kill all the tests first. Kill all tests. Good, they are all gone. All right. So we relaunch this. Relaunch. Yeah, just wait. Okay, we appear. The test guy will appear. Now, this is about the demonstration in this afternoon. In this afternoon, I show you another thing. The background process being killed. And what I'm doing, I'm in this shell. I press the termination of the shell, Command W, kill it. Okay, and in this time, the test gone. This is one thing about Mac. Okay, and if you want to know the answer is, it doesn't mean Mac sucks. Okay, Mac is sucks in this case. Well, what? Okay, Mac OS X 10 terminal 6 hop. Okay. I should face the closed terminal. Yeah, it's here. Can I say this? When you close a terminal window, it sends a SIG hop. Okay? So this is the important phrase. So let's take a look inside. Okay? So how to be basically is tell you that, oh, in Linux, in Solaris, it's not the case, okay? We close the terminal, it's still living in the background, very safe, very beautiful. In Mac OS, sorry, someone answered it. When you try to close that terminal, it will send you a SIG hop. So what is a SIG hop? Oh, why fixed signal becomes signal 1? Man 7 signal, no signal 1, okay. Yeah, I mean, okay, so SIG hop. Here, okay. Take a look at what is the description of SIG hop. It means hand up detected on controlling terminal or death of the controlling process. So what exactly it means? Hand up. What is hand up? You have a phone. You do this. It's hand up. This, I doubt whether you know what I'm doing. Okay, because in my child age, okay, we have a big phone. Okay, this is called hand up. Okay, yeah, you go home and take look at some old drama. Okay, then you know this is hand up. Okay, in the old days, terminal is connected to a computer, and there is a special signal to cut that cord. It's also called SIG hop. It's being inherited in Mac, but not inherited in Linux and Unix. Okay, so it's called SIG hop. And this morning I show you the SIG hop example. It's got get killed, but now I show you another version. If we know that it is because of SIG hop, we want to keep that process still in the system, then you should do this. Send in the background, don't kill the terminal, but type exit to close the shell. And because the shell dies, the terminal dies peacefully without SIG hop. Take a look. The test is here. So this is the main difference if you're a Mac user. You send something in the background, don't kill the terminal. Type exit, okay? If you are Linux, don't worry. Linux, you launch a background process, kill the terminal, no problem. If you're a Windows user, don't ask me, okay? I don't use Windows. Yeah, Windows sucks. Yeah, but in the kernel, what it's doing, very easy to understand, huh? In the kernel, it is running exit, this guy, running exit, and so happen that it's form a chain or linked lists, okay? A chain of parent-child relationship, a list of child pointer, because you may have more than one child, so I call it list of children, okay? Parent pointer, point to your parent, pause one don't have any parent. So you form a kind of seems to be double linked list, which is not. I call it a simple linked list or chain. Now you break the chain because you want to kill the one in the middle. And in the kernel, it's doing very simple way, is by looking at this guy. this guy had a list of children, and you go to each of the children, follow that pointer, which the child process, and for the child process, hey, now your old parent is gone. This guy become a stepmother, pointed to here, and I increase the number of child, okay, by 1. Okay, so in the kernel, it's just kind of easy to understand. Okay, so this hierarchy you have to understand, because if you understand this clearly, then you know that it works. You have infinite loop or something useful, send it to background, not close terminal if you're a Mac user, take exit, okay, and terminate your shell. Then it was still working in the background. And after some time you get finished, of course you have to use a redirection or save your data into the file so as to the process is stopped, okay? And you can still see the process running, just like what I showed you before. Okay? So this is observation number 1 by learning this process hierarchy. Second of all, you know that there's a big tree, okay? And there's a repairing things, that's all. Okay, the repairing phase doesn't anything really interesting. Okay, just tell you about this fact. Any question you want to ask? Any question you want me to try? No? All right. Yes. Yeah, you have to shout. Yeah. The program I run
in the shell.
In the shell.
It's first parent should be in the shell itself, right?
The parent is a shell, yes.
It's parent in the shell. So I think when the parent cross the dice,
I can hear you. Yeah, maybe we put it later. You come here and ask. All right. Yeah. So I'm also a deaf man here. Okay. So I pay too much band. Okay. So now another thing, which is very related to your life in this faculty, right? Your launch process. Okay. You want to know how a process should behave, right? And I think that you will get used to this diagram already. So what is this diagram? This diagram, you are in your mind, you already know about this, okay? But you never figured out that, oh, there is such a relationship, okay? You have a running state of a program, right? You put it in a CPU, it's run, right? And I call get char, waiting for results. Yeah, it's some stage that we call it is not on CPU. And after the results come back, it will go back to the running state. And then eventually, I don't know why, because of return 0 or you call exit, segmentation faults, whatever things you want to think of, eventually go to termination. Okay? So in your mind, it's something like this. But for the kernel, we have different view. Okay? The view is this. Even more bigger and more interesting. How interesting it is? Now, first of all, the waiting state, we no longer call it waiting. We give a name called block. Okay? Whenever a system call, that will block you. We call it a blocking system call. So what is the meaning of block? Okay? The block is very easy. You call a function, right? You call a function. That function so happen to be system call. That function go into the kernel, and the kernel don't let you go. Jail you, put the process inside the kernel code, never returns or return after a very long time, you get blocked. Okay? Of course, inside the kernel, you won't think of that, oh, is it because the kernel had a while loop? No. It's waiting for somebody else. So we call this kind of system call, enter that state, will bring you into that state called blocking system call. Okay? And there are 2 different states of blocks. Later on, I will tell you the differences. We have a big picture here. Some of you already know that, zombie state, I know, it means termination. What is this? To just fork, I don't know. Ready and 1A, what are they? Now we will go through it one by one. Just fork, you know what is that, okay? Because we already know about the hierarchy, we have an init. Init create a set of things based on the definition in that directory called /etc/rc.d. we will have a tree of things created by fork and execute. So the fork is the birthplace. After that, now why I write in this way? Because the fork itself is a big system call. It involves many things. It involves the duplication of a memory, duplication of the kernel space memory, user space memory, even some of the scheduling instruction. Maybe I want always the parent run first, okay? Then it's all happen inside this state. After that, we will go to a funny state called ready. So what is the ready? Ready usually are queues, not just one, okay? Usually many queues, okay? Queues for processes to state in the system, and when it stays in the system, it means that you're ready to run, but the CPU doesn't have the capacity. So you have to state in this stage, we call it ready. In the computer, where can you find the ready state? Let's take a look. So this command is called the PS, right? Your original process status. AUX, I have a big list of it. Pipe less. Okay, so these are the states. These are the states. So you can see many S here. Many S. Okay, well, what is SN? I don't know what is SN. Okay, many S, SL. Just a shirt size, right? And then we find one R. Okay, we have an R. Okay, so one of the S here, they are the main page called sleep. Okay, but I call it ready. Okay, these processes are all ready, but have no chance to run. And this guy is R. Why? This is the running program, running processor. And how about other states? Let's try this. Maybe I write a program is better. Write a program test.c, and then get char. Oops. Compile it. Now for computer, when you enter this state, you enter waiting for I/O. Okay, I put it in suspension mode. No, sorry, not top. PS AUX. So can you find the test? Yes. Now the test is here. Is have a T here. It means stop. Now why I show it to you? In assignment 1 phase 2, it's extremely important. You have to check. Oh, I do something. Whether that process is being released from certain states that I expect. I expect that it should be suspended, so I will find T. I expect that I send a SIG coin to that process, whether it will change from T to S or even R. Okay, so this is one very important place for you to check against whether you do something right or wrong. Okay, and here is a representation using 2PS. And illustration, just we call it ready. Okay, so the ready state usually enter the first thing after a fork is go to the ready, or you are going back from the waiting from the I/O. I/O means the input output, and then come back. The running, nothing, right? Just something on the CPU. Okay, the block states. Remember, usually block states because of blocking system call. It's never suddenly say that, oh, the blocking state does mean that I suddenly say that I don't want a CPU service, okay? Then I'm going into the block state. No, although there is a way that you can try to give up the CPU service, okay? I tell you what is the system call. You can use some time to read the main page, okay? It's called sketch U. Whenever you call it, it means that you don't want a CPU. But you are not exit the program. You are not going into suspension mode, but just, I don't want CPU. CPU sucks, I don't want it. Okay? Yeah. This is the system call, okay, called sketch U. Okay? But it's seldom implemented that way, and it is not a blocking system call. It means that you change from running to ready. Okay? And usually while you are doing the running, it's the entry point to either one of the block states, and it's always because of blocking system call. or a signal being sent to your process. And the two guys are kind of hard to explain. Okay, I give it the names. One is called interruptible system, interruptible block state. Another is called uninterruptible block state. Interruptible, like reading a file. You're reading a file, and suddenly you find that, oh, this is not a good process. I want to kill it. Press Ctrl C, it dies. It is interruptible. You can interrupt it, and it will be killed. And other type is uninterruptible. So what is the uninterruptible call? It means that it is doing something. You want to press Ctrl C to kill it, it won't respond. Okay? Did you ever seen this? How many of you have experienced that? You. What is the case? Okay. Good. Okay. Any other people have experienced that? You create a process, you want to press Ctrl C, it just don't die. Don't tell me that, oh, because I know Ctrl C. Okay, no. You accept Ctrl C, but you don't have any way to interrupt it. Okay? Usually, this is the case that process go into uninterruptible state. Oh, don't tell me this because of fork bomb. Fork bomb is another thing. Okay? Yeah, uninterruptible. I cannot explain to you because it's usually hidden in the kernel code. The kernel, let's say, the best example is fork. Okay? While you are doing the duplication of the process, let's say you duplicate two structure about that process, structure A, structure B created, without setting anything, you suddenly say that, oh, I don't do the fork, okay, Control C. What is the system state? I cannot explain, okay? What is the intermediate state during the fork, okay? So that's why fork is actually an interruptible blocking system call. It will finish from the start to the end and you cannot stop. Because in the intermediate step, it's hard to define what is should go on or not, or we unroll all the change, okay? Which is hard, okay? So I can only say that a process doing intermittent things, okay? There is an interruptible block state, and usually you will find it go to ready, seldom immediately go to running. Really seldom, okay? Then at last you will have questions that, hey, here is always running and then go to zombie, okay? Now the question is very easy to answer. Why you get killed? Okay, when you get killed, okay, you will have to execute signal handler. So that's why the signal handler so happen to be killed yourself, okay? So you kind of have a very short period of time on the CPU to execute something and then die. If something normal, return 0, except you have to run some code, so you will go to the zombie state by the running state. All right? So any question you want to ask? Yeah, this is something boring, right? And what is a scheduler? I didn't explain scheduler. I just tell you, oh, there's life cycle. The scheduler is, we usually have a bunch of ready state processes. Really much more than available CPU. I have an 8-core CPU, so what? Okay, I have 800 process waiting. Okay, the scheduler is to schedule who should go to the CPU and run. Okay, so this is the task. And also, there are multiple queues, multiple priorities. How can we put a process in a higher priority, or why I should put it in a higher priority, or not about priority? We have another bunch of processes, not in the ready state, but in these two states. Will the scheduler look at them? We don't know. Okay? So, next time, in the coming Thursday, I don't want to bore you to death, okay, although I have 15 minutes more, okay? We will talk about one important job that CPU try to switch from one process to another. That role, or that set of procedure, we call it context switching. We will talk about this very important page. I don't want to bore you because this is very important. I want you to have the best possible mind to understand this. Basically, is the moments that a CPU may step in. Oh no, sorry, not CPU may step in, scheduler. The scheduler may step in. We may have possibility number one, you use up your share on the CPU. Then scheduler step in, so this is scheduler color. Second, hard disk or I/O, you give up the CPU. Then, because you want to wait for something, scheduler step in. Termination, scheduler step in. So we will try to spend 5 more extra minutes on first day to reinforce this concept. This concept is very important because later on when I talk about different features, hey, why I have a scheduler suddenly gets triggered is because of either one of this case above. So I put down a tag here, very important. Okay? So we'll come back on Thursday and talk about the scheduler. Okay, thank you. See you later.